Well, hello, my name's Jared, and today's lecture is about stability. I've broken the stability lectures into different chapters, so it makes it a little bit easier for you all to follow. The lecture tends to follow the book, and there are a number of activities within that book that you can do in your own time. And that's important so that we can ascertain whether you're keeping up, or when we have a get together on social media or Zoom, then we can talk about any issues that you have. So let's get started. So the first one is managing stress and dynamic factors affecting a small vessel stability, and we're talking about basic principles of stability. So the objectives for this one is to interpret basic stability information. So principles of stability, terms and definition, relationship between weight and buoyancy, reserve buoyancy, equilibrium, impact of design and the hull shape on stability. We've got to manage stability, so we're adding and removing weights, water on deck, slack tanks, different roll periods, different tender vessels, additions and alterations to the vessel, stable and unstable vessel list and trim and water density. So there's quite a bit to cover in the Master 35 Stability. This is backed onto what you've done in your Master 24 Stability, whenever that was, either a few years ago or a long time ago. So there's a lot of stuff that we cover, and make sure you come up to speed with what you already have done in the past. And also it's important to try to think about how your vessel reacts in the way of stability. And a lot of these things that we talk about, you'll look at it and go, oh yeah, that's how my boat works. So it's kind of the theory behind it all. We've got two assessments in the 35 Stability. One's a stability written exam, and the other one is a cargo assignment. And the cargo assignment takes into both stability and also obviously cargo and loading that ship. So some definitions to get ourselves started. Light displacement, weight of an empty vessel. It includes the weight of the structure, fittings and machinery. Load displacement, weight of the loaded vessel or loaded with people, baggage, fuel, water, cargo, stores, etc. Dead weight is the weight of people, baggage, cargo, fuel, water, stores that can be carried on a vessel. And it's difference between the two above, the load displacement and the light displacement, is your dead weight. Draft is the vertical distance from the keel to the waterline. Freeboard is the vertical distance between the waterline and the freeboard deck. Heel is the inclination of a vessel to one side under the influence of an external force such as wind, waves. So it's out of our control, is a heel. A list, inclination of the vessel to one side under the influence of internal forces such as uneven distribution of weights within the vessel. And that's up to us to manage that weights on board our vessel. Trim, inclination of the vessel in the longitudinal direction. It's measured as a difference between the forward and aft draft. So if we put a weight on the bow, we're going to trim by the bow. If we put it down the stern, we may trim by the stern, depending on the size of the weight. Right, so what's stability? The ability to control the vessel to return the upright over. And we should always have forces. If we look at this back here, plays background, go to C, and now we'll see how to press our transit. We want to have enough stability to rough weather to be able to be safe. Sure they weren't having much fun on that ship in that sea state. All right, so why do some objects float in water and others sink? First, we need to understand the relationship between the volume, mass and weight, and the forces of buoyancy experienced by an object placed in water. So volume is a space occupied by or contained within an object. The most common unit of volume are cubic meters and litres. A cubic metre is a volume of 1,000 litres. Mass, the mass of an object is the amount of matter or stuff it contains. The more matter an object contains, the greater the mass. So an elephant contains more matter than a mouse, so it has a greater mass. Mass is measured in kilos or tonnes. 1 tonne is same as before, 1,000 kilograms. A 100 kilo object has a greater mass than a 5 kilo object. And remember, an object's mass stays the same wherever it is. Weight is a force caused by gravity. The weight of an object is the gravitational force between the object and the earth. The more mass the object has, a greater its weight will be. And weight is a force, so it's measured in newtons. On the surface of the earth, an object with a mass of 1 kilo has about the weight of 10 newtons. Remember that mass is measured in kilos and weight is measured in newtons. Well, it's important to know the difference between mass and weight. In keeping with industry practice, we should use the term weight rather than mass. All right, so there's a number of activities in the book that you can do, and I asked you to complete those so that when we do actually get together, I can review those stability books and we can see where we're at to, and it gives me a bit of an idea of how you're actually going. So we won't actually talk about each of the activities on the presentation, but please do them. You can pause the video and do that, and then and the answers are in the back of the book. So there's the first activity for you. All right, so relative density. So we all talk about specific gravity. It's very similar to relative density. We know that diesel, we throw diesel on the water. What happens? It's lighter than water, so it floats. And that's all that to do with specific gravity. So this gentleman here talks about that.
Hi, I'm Steve Jones, and I'm going to explain what the specific gravity of water is. It's quite a strange question because specific gravity relates specifically to water anyway, but I'll explain that in a moment. First of all, let's take a 1 centimetre cube. 1 centimetre by 1 centimetre by 1 centimetre. So its volume is 1 centimetre cubed. So the volume is 1 centimetre cubed. Now, the mass of this cube will be actually 1 gram if it is water. If this is a cube of water, then its mass is 1 gram. So, because we have this quantity density, it's density which is important in this case. Density is how heavy something is. So density is mass divided by volume. The mass is 1, the volume is 1, and that gives us a density of 1 gram per centimetre cubed. That is the density. Now, specific gravity, as such, is slightly different from density and much more useful, because specific gravity tells us how much heavier some material is compared to water. So it is not how many grams per centimetre cubed, it is a number. It is a ratio. So it is the mass of a cube of whatever substance you're interested in divided by the mass of water. So the specific gravity of water is the mass of 1 centimetre cubed of water divided by the mass of 1 centimetre cubed of water. And something divides by itself, the answer is 1. Of course, water is the standard. Water has a specific gravity of 1. So that is what the specific gravity of water is.
There you go. And I think he describes that very well. So the weight of a cubic metre of any material is called its density. For example, 1 tonne of fresh water has a volume of 1 cubic metre, therefore the density of fresh water is 1.00 tonnes. Relative density is comparison between the density of a substance with the density of the water. 1 cubic metre of salt water weighs 1.025 tonnes. So salt water has a relative density of 1.025, so it's more dense than water. So any kind of density of water between fresh water and salt water is called dock water. And water density will vary between 1.025 kilograms, or relative density 1.025, of seawater and 1,000 kilograms, and a relative density of 1 of fresh water. A mix between fresh and salt water or seawater is called dock water. And as we go through the course, we have to work out what the relative density of some of our dock water is, and we can do that. There's the activity 1.2, so have a go at that one. Pause the video and do that one. All right, so the laws of flotation. Archimedes' principle: when a body is wholly or partially immersed in a liquid, it appears to suffer a loss of mass equal to the mass of the fluid it displaces. So he worked that out. He put himself in a bath, and he measured the amount of water, or the weight in water that flowed over the bath, and that weight of water was equal to his weight. So a ship does the same thing. An object is plunged in a fluid, becomes lighter by the amount equal in weight to the fluid that it displaces. So a ship will float once it displaces the amount of water that the ship weighs. As long as it can do that, it'll float. Objects float when it can displace its weight in fluid without submerging. A floating vessel displaces a mass of water equal to its own mass. Even if a vessel is whole and filled with water, she will float if there's enough air trapped in it, or it's flooded with enough extra buoyancy, such as foam or bags. This is simply because her total weight does not exceed the weight of water she displaces. So we've got two little boxes here. One on the left, a solid box of steel that measures 1 cubic metre and weighs 4,000 kilograms. It's lowered into fresh water and it displaces 1 cubic metre equal to 1,000 kilograms. So you can see that once it does that, it's displacing 1 cubic metre or 1,000 kilograms. So the overall weight of that box once it's in water is 3,000 kilograms. So it's got lighter because it's displaced 1,000 kilograms. On the other side, the same block that's moulded into a hollow box with a volume of 4 cubic metres, lowered into fresh water, it displaces 4 cubic metres of water. So it will just float. Activity 1.3. All right, so in the book it has lots of diagrams like this. So let's just explain the diagram so you can follow it in the future. The WL on there is the waterline, and it's the waterline where the vessel is floating. Down the bottom, obviously, the keel, or the K is the keel. B is buoyancy. And this is the center of the underwater volume of the vessel, and it's called the transverse center of buoyancy. And it's the point through which the forces of buoyancy act vertically upwards. Transverse because we're looking at it from either the stern or the bow, so transverse, as opposed to longitudinal, looking at it from the side. Gravity is the center of gravity, and it's the point of the overall weight of the vessel, and therefore the point through which the weight of the vessel can be considered to act vertically downwards. The vessel is floating with part of its hull submerged and part outside the water. The weight of the vessel is supported by buoyancy, which is equal to the weight of the water being displaced. If extra weights are loaded on the vessel to increase its weights, then the enclosed spaces will provide extra buoyancy required. So then there's a little animation there. You can see if we put a new weight on the boat, then we will have to disperse the same amount of weight in water, and obviously our draft will increase. So tonnes per centimetre. So when weights are loaded on a vessel, its draft will increase. On the other hand, when weights are discharged from a vessel, its draft will decrease. So the tonnes per centimetre, or TPC figure, is a calculated measurement adjusted for any draft of a vessel. To give the amount of weight in tonnes, which must be added to or removed from a vessel to change its draft by 1 centimetre at the draft level. The tonnes per centimetre calculated figure corresponding to the vessel's various draft level can be found in the hydrostatic particulars given in the vessel's stability booklet. All right, so at the moment you've got 2 books. One is the Learner Guide for Stability and one is the FV Tamar Stability book. In the back of that book, on the last page, it has those hydrostatic particulars for that particular vessel. And you'll see in there, it's one of the columns has TPC. For this particular picture or the PowerPoint, this is just, it's not the one out of the book, it's just one that's been made up. But you can see here, it's got a draft on the left-hand side. So reading at the draft, so it goes from 0.7 to 2.1. And then the next one is the displacement in tonnes, so how much the vessel weighs at a particular draft. So if it's at a draft of 2.0 metres, you can see that its displacement or tonnage is 373 tonnes. So it's displacing 373 tonnes to get it to a draft of 2 metres. And then the last one, the tonnes per centimetre. So how much weight do we need to put on that vessel to change its draft by 1 centimetre? So you can see the first one at 0.7 metres, we need to put on 1.7 tonnes to change its draft by 1 centimetre. And that increases as the draft increases because of the shape of the underwater hull. So there, on the bottom there, note the vessel's displacement and TPC can both be obtained if the draft is known. So the hydrostatic tables is based on the vessel's hydrostatic draft or the true mean draft, which is the draft at the centre of the flotation. The centre of flotation is the centre of the shape of the waterline or the water plane area at which the vessel is floating. For small vessels, the hydrostatic draft will not differ significantly from the vessel's midships draft or the mean draft calculated by averaging the forward and aft draft. All right, so if we're sitting at a draft level, somewhere in that, if we cut it off with a chainsaw, at the draft level is the longitudinal center of flotation. So that's where it's going to pivot for the bow to the stern with its trim. All right, so calculating TPC, so we can actually work out how much weight we can put on or take off to change its draft. And it's the TPC calculations to find the body shrinkage or rise due to loading or unloading weights is applied by the following. Body shrinkage or rise, well, that's just draft, increase or decrease, is weight divided by TPC, or weight divided by TPC. This calculation will determine the amount of centimetres rise or fall from a particular weight being discharged or loaded on a vessel. All right, so there's an activity. So refer to the hydrostatic tables in Appendix D of the FV Tamar book, so the other book you got there, and determine the TPC for the following drafts. So all you have to do is find out what 2.5 and what the TPC value is for that one, and 3.3. A similar formula to that for body shrinkage rise can be used to determine the amount of cargo needed to be loaded or discharged to achieve a desired draft or displacement. So that's weight required for a draft change and draft alteration multiplied by TPC, or draft times TPC. This calculation will determine the amount of weight required to alter the vessel's draft rise or fall by a given distance. All right, so here's a bit of an idea of how that works. The FV Tamar is floating at a mean draft of 2.5 metres. What will be the new mean draft if 6 tonnes of cargo is loaded on board? So we go to the hydrostatic particulars in the back of the FV Tamar book for the TPC at the draft of 2.5. And we see that that is 1.2 tonnes. So we go down to draft, 2.5 metres, go to TPC value, and you'll see that it's 1.2 tonnes. So 1.2 tonne has to be added on it to change the draft by 1 centimetre. So there we go, body shrinkage. We need to put on 6 tonnes because that's what the question asks. And we know that at our current draft level 2.5, our TPC is 1.2. So if we divide the 6 tonnes divided by 1.2, you can see that our draft will change by 5 centimetres. In other words, the draft will increase by 5.0 centimetres or 0.005. I think the second one's the most important one, at 0.005, because you can get mixed up if you put down 5 centimetres. So therefore, the new draft, we were at 2.50 metres, and then we added 5 centimetres or 0.05, and our final draft is 2.55 metres. So have a go at that activity there. That's in your book to work out those TPCs. The next one, a vessel has a mean draft of 3.2 metres and the TPC value for the hydrostatic particulars is 2.1 tonnes. Calculate the amount of weight required to increase the vessel's draft by 6 centimetres. All right, so we know that our mean draft is 3.2 and the hydrostatic particulars, the TPC value is 2.1 tonnes. So that is draft times TPC. So our draft at the moment, we want to increase the draft by 6 centimetres and the TPC is 2.1. So if we times those together, we'll find that we will have a new weight of 12.6 tonnes. So we need to put 12.6 tonnes on there to change its draft by 6 centimetres. Therefore, the weight required to increase its draft by 6 centimetres is 12.6 tonnes. All right, so let's say you're a cargo vessel, you're sitting alongside the wharf and you go and look at the draft marks and you can see you have a bit of a guesstimation from where the draft is at the moment, where your load line is, it's 6 centimetres. So instead of saying to the crane driver, yeah, keep adding, you know straight away, you can tell them, put on 12.6 tonnes or 12 tonnes or whatever the case may be, and you'll know that you'll be in the ballpark. When loading and discharging relative large amounts of weight, that will have a significant effect on the vessel's draft. Masters and crew should refer to the displacement tonnage and draft figures provided in the hydrostatic tables for that vessel. A comparison between the displacement figures will determine the amount of change to a vessel's draft when loading or discharging that amount of weight. All right, so that means, let's go back. If you've got to change its draft by a lot, you can just go to the tonnage ones, and I think we go over that in a minute. All right, so there's 2 types of displacements. We've got our light displacement. You can see by the Maersk there it's got no cargo on it, so you can see the cargo line or the load line's very high, and then our loaded displacement is the other one where all the cargo is put on board. So the light displacement, when a vessel is empty, i.e., just going to move that, i.e. the vessel only consists of the hull and the superstructure, and machinery is said to be floating in a light draft, and therefore it's light displacement. When a vessel is fully loaded with fuel, cargo, etc., it's said to be at its load draft and is therefore its loaded displacement. Obviously, the freeboard of the vessel will be less in the low displacement condition than when the vessel is in its light displacement condition. The difference between light displacement and low displacement is called dead weight. And we talked about that right at the second or third slide when we talk about these different terminology. Dead weight is difference in weight between an empty ship and the same ship in a loaded condition. Dead weight is an indication of the amount of cargo fuel, fresh water, ballast stores, etc. that a ship can carry. So we'll quickly do this one. A vessel's light displacement is 50 tonnes and its low displacement is 85 tonne. What's its dead weight? So it's light displacement, it weighed 50 tonnes. Then we put all the cargo on and its low displacement 85 tonnes. So how much cargo did we put it on? Fairly simple maths there, 35 tonnes. All right, so in the book, there's progress checks at the back of it, or where you're up to right now. And so I ask you to complete those progress checks to make sure that you have a bit of an understanding of what we've actually covered through that first chapter. So there it is on page 18, 19, and at the back of the stability book gives you the answers. But definitely complete those, and we'll get on to the next chapter.